I should probably first introduce myself. My name is Christopher Diggins. I work at Microsoft, but don't actually work with languages. I write documentation. Languages is something I do as a hobby, so I'm rather an oddity here. This presentation is probably going to set a new record for slides per minute. I'm going to try and hit about 100 slides. So unfortunately, there's not going to be any time to answer questions. And I know there's just about 1,000 questions everyone could ask me. But please feel free to approach me at lunchtime or anytime thereafter and talk with me about this. Besides, I think your answers to the questions that you may have will probably be more interesting than my answers. As I'm saying here on this slide, I'm just trying to provide a new viewpoint onto the ideas of optimization and low-level representations of languages. So I'm just trying to encourage discussion. So CAT is a stack-based functional language, and it's designed to be a layer between multi-paradigm languages and the MSIL, or other low-level targets like assembly. I designed a relatively obscure language called Heron. It's not terribly exciting. It's mostly a C++ clone. But in order to go further, I wanted to target it to the MSIL. But I thought, well, why just solve the specific problem of targeting the MSIL? Why not write a general purpose intermediate level language that I could optimize and also serve as a macro language? So usually I have to answer the question, why did I reject prior art like other low-level representations for optimization like C++ or LLVM, etc. I found a lot of them miss opportunities for functional optimization. They're also not well suited for parallelization, and of course it's fun to invent things. I had a few observations when I started the design of CAT, and one of them is that a lot of imperative code can benefit from being rewritten as functional code. I also noticed that a lot of low-level representations leave out functional primitives like map or filter or reduce. And so I wanted to make sure I included that as atomic operations. I also noticed, of course, that pure functions are more easily parallelized. So I wanted to make sure I identified snippets of code which are pure and which could therefore be parallelized. And of course, it's also easier to manipulate code that has no variables or named parameters. So CAT goes ahead and actually has no variable declarations, no argument declarations, high-level functional primitives, static typing, a pattern rewriting language, and very simple syntax and semantics. Unlike other low-level representations, it's actually intended for human use. So as a result, there's namespaces and type annotations. I found it's just easier to work with, and it's easier to reason about and extend, and to build custom libraries for. There's two major influences to the CAT design. Joy, which is a very obscure language by a fellow named Manfred von Thum in Australia. And of course the MSIL was highly influential. But of course between those two languages are countless other languages like FP and Scheme and Forth, and they've all come to play in the design of CAT. There's one way to describe CAT as a compositional language. And it can be differentiated from functional imperative languages, which are more examples of applicative languages. And there's some people out there, there's some communities which call languages like CAT and Joy concatenative languages. As far as I'm concerned, it's all just semantics, and it's of little consequence. So CAT is based on the composition of functions. If you have two commands in CAT, F and then G, assume the user-defined functions, they have the mathematical meaning I think that's G composed of F. So as a result of its being a composition language, it uses postfix notation. Here the braces just indicate scope, and they're also used to group things. Another thing we'll come to later on, though, and I should probably point it out now, is that 1, 2, and 3 are not actual values. They're the functions which put on top of a stack the values 1, 2, or 3. That becomes important later on. I'm going to skip this slide, but it just shows the equivalence of these different programs. CAT is based on the concept of stacks, like the language Forth. There's two stacks. There's a primary stack and the auxiliary stack. And this actually maps quite closely to the MSIL. The auxiliary stack can be thought of the list of locals, and the main stack is just the evaluation/call stack. A CAT program is a concatenation of 0 or more atomic programs and or user-defined programs. And this is why some people call them concatenative languages. So every program can be viewed as a function which maps a pair of stacks onto another pair of stacks. Of course, only pure CAT functions, those with no side effects, are actually comparable to mathematical functions. So I have to introduce a few concepts. One of them is consumption. So every stack program consumes either one or both of the stacks, the main stack and the auxiliary stack. Every CAT program, this is part of the semantics of the language, is that it must consume a constant number of elements of fixed type. Of course, there's no peaking. You can never look below the number of elements it consumes, but that's the definition of consumption. And of course, we also have production. It leaves results on the stack, and it can leave multiple results. And the same as consumption, it must always produce, every program must produce under all circumstances a constant number of elements of fixed type. There's another concept of valence. If you produce and you take the number of elements produced minus the number of elements consumed. So imperative control structures like while and if often have a valence of 0. So here's a couple simple examples. AddInt is a function. It consumes 2 integers, produces 1 integer, so it has a valence of -1. Swap consumes 2 values and produces 2 values. It has a valence of 0. So as a result of the consumption and production rules, you always know what this state of a stack is. It's never ambiguous. Most CAT programs only operate on the main stack. And the original design of CAT actually only had 1 stack, but I found it much easier to map to languages like the MSIL if I introduced the idea of a local stack. And I'll come to that later on. CAT, I divided up the idea of CAT programs into functions and subroutines. The functions are the CAT programs that only consume and produce values on the main stack. Let's say a program manipulates something on the auxiliary stack, you can manipulate, but if you you have a net consumption or a net production on the auxiliary stack, I call it a subroutine. As a result of the idea of consumption and production, you can actually consider a CAT function to be just like a regular applicative function, a function in an imperative language or a function in a functional language. So the stack consumption is your arguments and the stack production is your results. Again, I already defined what CAT subroutines are, so we'll skip this. Oops. Sorry. So there are several built-in or primitive functions, which I call atomic functions because they can't be subdivided. They aren't pinned down precisely. It's a constantly moving target, and I think it should be defined by the language that CAT is targeting. So the purpose of CAT is to be a multi-purpose intermediate level language with constant syntax, constant semantics, but the level of primitives, the core language operations are going to be defined by the person using or implementing stack, CAT. So like Forth, you're going to have a bunch of stack manipulation functions at the base level, and this is just every implementation of CAT would likely have things like pop, or duplicate, upd, which means duplicate the second item in the stack. And then we have the various rotation. These are all what we call shuffling operations, just for manipulating the stack. Of course, we have a whole list of arithmetic functions, which consume values off the top of the stack, and most of these produce one value on the top of the stack. Except for something like divmod, which is a bit of a rarity. It will divide and do the modulo at the same time, so it produces 2 results. Same. In CAT, you can use symbols as names, as identifiers. So of course, I said before that I wanted to have the functional primitives. So we have, the usual suspects of list functions: consts, unconsts, head, tail, rev, count. The list goes on. We all know what they are, hopefully. Whoops. As I said before, literals are programs which push values onto the main stack. So they always have a valence of 1. And some examples are 42, the string hello, 3.14. But these are programs, not actual values. As I mentioned before, there's concept of scope and namespace, which are marked by our friends the curly braces. The difference, there's no real difference between scope and namespace as far as I'm concerned in CAT. The namespace is simply a named block. I'm sorry, so far there haven't been many examples of code, and soon you'll have way too many examples. But first I want to introduce the concept of an anonymous function. This is crucial to CAT. So in your square brackets here, where you see 1 plus, that's a lambda expression. So what this does is it pushes the function successor, which is add 1 to the current value. It pushes the function onto the stack. I executes the function on the top of the stack. So it's called a combinator because it's a function which operates on functions. You could call it a higher order function if you want. So the result of this expression is 42. So there's no actual syntax for lists in CAT. So what you have to do is use a list eval operator to take an anonymous program, and what it will do is produce a list and put that on top of the stack. And of course there's a shortcut, because who wants to type 9 characters when you could type 1? How do I explain that? So of course there's named functions. Named functions are crucial for humans writing code in CAT. So it's as simple as saying define f as being function 6, 7, multiply, which obviously produces 42 on a stack. So of course there's control flow, but that's done functionally using functions like if, which takes 2 functions and a Boolean value on top of the stack. So if is a ternary function. It requires 3 arguments: a function, and a Boolean value. There's also, for looping, we have while functions. And while takes 2 functions as parameters. The first function is the loop body, or the loop variant, and it must have a valence of 0. And the second function is the loop invariant, and it must produce a single Boolean value. All of these rules are actually expressed in a type system, which I hope to get to soon. So here's an example of using the while function in CAT to produce a factorial. This is rather nasty. And I'm not actually going to even bother explaining what all of this means, because first I'd have to tell you what dip does. And, well, dec is obviously subtract 1. But understanding that it's a real brain teaser, the first couple of times I wrote it, I was wrong. And this is probably still wrong, too, because there's better ways to do it. There's comprehensions in CAT. So we have a couple of built-in comprehensions, n, which outputs the list of the first n natural numbers. So it requires a single integer value on top of the stack. And then it will produce a sequence of natural numbers. And of course there's init, which applies a function successively over and over to a value to produce another list. Again, you would use these to produce lists. So using the n function, here's how we can produce factorial. So the question here is, looking at this, isn't this expensive? Because doesn't n produce, a list in memory? Well, I figure why? Why should it bother creating a list in memory when you could just use a generator function? So we have the notion of selective laziness in CAT. And it doesn't change anything whether an implementation decides to use selective laziness or not. It's just smarter. Sorry. So a pure function is a function which is referentially transparent, or a function with no side effects. So it can be replaced with any other function, any other pure function generating the same result. So I notate that by saying that the function, the composition of 1, 2, and plus could just be replaced with 3. And this is key for the optimization engine that we'll get to soon. Of course, there's going to be impure functions. Any worthwhile practical programming language must have side effects. You have to read and write to the file system if you want to do anything practical. But we can still restrict it, and we can still identify it, and that's the crucial thing to dealing with impurities in a language. So you have things like read, write, rand, which generates a random number, time, which gets the current time. These are all impure functions. One thing we'll notice about impure functions is that they're order dependent. You can't just rewrite these things and shuffle them around. You have to execute them in order. Other functional languages have solutions like monads and arrows. We just notate them specially and say, don't shuffle this. So, like I said, impure functions can't be rewritten easily. Order is important. So what's crucial is identifying them. Here's an example of how we can kind of identify it. So let's say I define a function f, and it's the compose of these 5 functions. Well, as I was showing you the equivalency rules before, we can define a as being the first half, b as being the third half, like the last part. And then you can redefine f as a, g, b. So then you can work with optimizing f0, and then after that you work with optimizing f2 and f3. All right, this is where things get interesting and where I'm starting to branch a bit from previous work, because languages like Forth and Joy don't have a strong type system, and they don't have type annotations. Forth has an interesting comment structure, a way of saying what you're trying to do, but it's not actually type checking. What I did with CAT is devised a type annotation system and strong type checking. So in this example, what this says about f is that it's a function which consumes 2 integers from the stack and produces a single integer on the stack. So it's, again, a valence of -1. Type annotations. Well, you can always infer the type, but I found that type annotations are extremely useful because they document what your code is doing, and they allow you to catch bugs. And as a developer who's not too bright, I'm always making bugs. So I desperately need a type annotation system in my language. You can also label your type annotations. So you can add variables, which essentially looks like argument names. When you look at it with a type system, you know that there's only one interpretation. Throw away the y on top and just leave the first value. So, as I said before, there's an equivalency between applicative languages and compositional languages like CAT. So, given some C#, C++, Java type language where you have a result, return type, function name, argument type, argument name, argument type, argument name, you can rewrite that function signature in CAT as follows. That should be self-explanatory. Now, list annotations are useful, especially when you look at them in the context of these list functions. Here's something I did in CAT, which is perhaps, disagreeable to some people. I have head and tail, and I also have first and rest. Typically, these mean the same thing. Head and first will mean the same thing, and tail and rest will mean the same thing, depending on the functional language you're using. But I wanted to express the fact that one of them left the argument on top of the stack, and one of them didn't. But looking at the type annotations, we can automatically see what the difference is between head and first are. And I don't need to document it once you've learned and familiarized yourself with the type annotation. These are list indexing operations. I'm going to skip over this. So here's the impure type annotation. I said it's important to label what is impure in your language. And so I use a squiggly arrow. So this is still used for static type checking, but it indicates to the compiler that it's not going to be able to shuffle this around. It's going to have to execute all impure functions in order. I don't have enough time to talk about type inference, and besides, that's a kind of a crappy pseudo notation for type inference. But you can take my word for it that it's possible to infer the types relatively easily. Now, I talked about an auxiliary stack. All of my operations up so far have just been on the main stack. But, of course, there's a second stack. The extension of the annotation is obvious. You'll see it here. This explains this shows that we just have two stacks now. This main stack, this auxiliary stack, and this main stack, auxiliary stack. But this is imaginary. We don't need this. Let me come back to here. What happens is the auxiliary stack is used for locals. And in a function, you can easily have hundreds or thousands of locals, especially when you have nested functions. So it becomes impractical to annotate all of the effects locally. It's used by the type inference engine, but it's not expected to be used by programmers. So I'm just leaving it out of the language. Nonetheless, I can still use it to talk about how things map to pure functions. Now, so the subroutines are the programs of cat which manipulate the local stack, or auxiliary stack, if you will. And there's only two of them, load and store. But there's a whole sequence of them, load number n, so where n is some integer from 0 to 32,000, assuming that's your upper limit for the number of locals you can refer to. So what load does is just like load lock in the MSIL. You move from the main stack and you're pushing it into the auxiliary stack. Nope, sorry, load is the opposite. It stores the other way. So here's some annotations to show you how load number 0 works, load number 1 works, load number 2 works. And I'm running out of time, so I can't explain all of it to you, but you can look at the slides afterwards and try to figure out what the heck I was talking about. And there's store. Imperative to functional. So my assertion is that you could take an imperative code like this, int x, y, x equals 6, y equals x times 7, and you can translate it to a bunch of pure functions which are composed. And this is it. And I've annotated it. This is cat. So what we took is the pure imperative code, a bunch of assembly instructions, and here's the pure notation of each function. So imperative code can be seen as a composition of functions which map pairs of stacks onto pairs of stacks. I think this is significant. I could be wrong. Combinators are functions which take functions. I've already said that. There are type expressions for combinators, so I don't have time for this. Sorry. The I combinator, I told you what this one does. It takes a function and it executes it. It's very simple. That's the type annotation for it. If is a combinator. Dip is a combinator which hides the top of the stack and replaces it after it finishes executing the top of the stack. Dip is very useful because with dip you can eliminate the auxiliary stack. And this is how languages like Joy operate. They only have one stack because they use the dip combinator. What is interesting about dip also is that to implement it, you need a secondary stack. So this is where I kind of diverge. Well, one of the places where I diverged from Joy, I said, well, let's just give a whole secondary stack. But here's the code in cat, which I can use to implement dip. There's app2. I don't have time for that. And of course, there's just countless combinators you can think of. And Joy has a few interesting ones, and one of them is called binrec, which is the binary recursion combinator. And it takes 4 functions, and it does a binary recursion algorithm on them. So this is actually a definition of quicksort using binary recursion. I stole that off of Wikipedia, but it actually works in cat, so that's fun.
What would you use, cat?
That's a good question. We can talk about that offline. Okay, the question was, where would we use cat? Let me get to something really quickly. I only have like 5 more minutes here. So I'm going to get to the transformation engine, and then maybe you'll get some ideas from that. There's a transformation engine in cat. A lot of patterns can be rewritten more simply. 0 plus, just be dropped out. 3 pop, it's a no-op. Lots of no-ops like that. In cat, there's something called a transform. Transform, this is actual cat syntax. you can express a transform which changes from one function to another. Transform works like a pattern matching macro system. Now, these are some really naive ones. There's some really more interesting ones coming up. Maps. How about the fact that maps are distributive? This is where things get interesting from my point of view. When I see code like fmap, gmap, as a human being I know I should have written it like this. But this can occur because of function inlining or whatever. But in cat, we kind of save ourselves because we have a transform already written, which whenever it sees this pattern in code, after inlining, it produces this, which is obviously a lot quicker. That's just one transform. There are hundreds or thousands I can think of, and they get increasingly interesting. Map, filter, filter maps, filter reduce. I'm just trying to find a really good example. Map reduce, here's an interesting one. This transform reduces a map operation, map, and then a reduce operation into a single reduce operation. So to wrap up, and I know clearly I have too many slides and not enough time, but to wrap up, the question I think is a worthwhile one to answer is, where would you use cat? Well, you'd use cat if you've got language which is either imperative or functional, and you want to apply transformations like this in order to optimize, and you want to express your transformations automatically. Rather than just writing a bunch of code to do all of these things, you can actually express it in a library of macros. So that's sort of the hope.
So Chris, the transformations would occur on the emitted code. We're not talking source code. We're talking emitted code.
No, actually it occurs on source code. Yeah. Well, source code's neat because you just run through it. What cat does is it inlines everything that it can, and then it starts applying transforms. Just keeps applying transforms over and over again until it can't reduce anymore. It's two kinds of transforms, and I didn't get to them here, but there's two kinds of transforms. Ones that are clearly good, you want to go in that direction. Some which you might want to go if it gets you to where you want to go. So it becomes a search in kind of a graph space of like, oh, can I get to a place where there's fewer operations and more efficient operations. So the idea, though, is that the transforms are actually operating on source code, and they're really trivial to implement transforms. So I think this is a result of the fact that it's a compositional language. And that's where I'm sort of thinking it's like, if I tried to write this stuff out in Scheme or Lisp or whatever, I wouldn't be able to do it, or even Haskell. But writing it out in this kind of postfix notation, and without the variable arguments, and it all of a sudden all falls together. So the open question from my point of view is, can I express all of the common deforestation algorithms that exist? Can I express them all? Can I express them all as transforms? And that's where I'm going with this. Anyway, thanks a lot very much for your time. And if you want to talk about this or you have ideas to suggest to me, please feel free to approach me at any time.
Mostly scientific calculations kind of things, algorithms, complex algorithms, application area, these kind of things.
What is the
application area? Which kind of programs I will code? Like scientific algorithms, heavy scientific calculations, complex.
No. Well, okay. The question is.
The question is the application area of cat.
Yeah. I don't know if I have time to answer the questions. Do I? Do I have time to answer one question? So the question was, what is the application area of this? As far as I can tell, it's anything. It really is. All of the code that I've been able to write in Heron can all be optimized to some degree using these algorithms. I'm sorry, I can't really answer any more questions I've been asked to.
Actually, I was going to offer an example of where I think you might be able to use.
Oh.
Okay.
So.
What I see, correct me if I'm wrong,
Hmm.
you could use it to optimize source code before you use rules that are defined by like FX output. Like you can think in an implementation of like a collection of things you find there, and then you can run through your source, and then optimize your source before you go and compile it, and the result would be like FX compliant code, whereas beforehand you might have analyze very code that would not optimize IL.
So the solution being proposed here is that it could be used with FXCOP to optimize existing code based on the rules, yeah. But anyway.
Or you could write a plug-in in doing the generate it first, and then compile. Kind of like script starter.
Thanks.
Well, thank you very much for your time.